and all attendees for this interesting session about the water, food, and energy. Dr. Hisham Al-Dabiri, Kamran Sumoro, and Mr. Muhammad Noer. I would like to present myself first. My name is Muhammad Daoud. I'm a professor at National Water Research Center. I'm the chairman of the session today, and I'm working at present as a senior water resource officer at Abu Dhabi government in United Arab Emirates. We have three presentations today. The first one from Dr. Hisham Al-Dabiri, and it's about the one of the hottest topic now. It's about GERD, which is the Grand Resonance Super Resonance Dam, and Dr. Hisham will speak about the blueprint for the adapting highest dam operation in Egypt to challenges of filling and operation of the Grand Super Resonance Dam. I would like to introduce first Dr. Hisham Al-Dabiri. Dr. Hisham Al-Dabiri is a PhD candidate in the Civil Environmental Engineering Department at the University of Washington, United States. Dr. Hisham received his bachelor degree in science with a degree of honor in civil engineering from Alexandria University in Egypt in 2010. Dr. Hisham received his Master of Science degree in civil engineering at the University of Louisiana in 2014. Hisham also primary research focused on his find sustainable solution for the challenging facing the food, energy, water NEXUS through or in the transboundary basins. Dr. Hisham has been served as a part of the American Geophysical Union, AGU, Technical Participation Committee since 2018. Hisham is currently working on his PhD, and we also wishing him all the success. I think this is not the first presentation I attended to Hisham. I attended to him one or two even presentation before. So you are welcome, Dr. Hisham, and you can start presenting your presentation. Please, the floor is yours.
Dr. Mohammed, yeah, I just start sharing my screen. Okay, thank you very much, Dr. Mohammed, for the introduction. So I'll be presenting today on a satellite-based framework or blueprint on how to adapt the reservoir operation to the challenges in the transboundary basins. And the case that I'm showing today is, as Dr. Mohammed mentioned, is to adapt the highest one dam, for example, as an existing reservoir in the Nile Basin to the challenges of the filling and operation of a planned dam, or it's a dam which is currently actually under construction, which is the Grand Ethiopian Renaissance Dam in Ethiopia. So first, quick overview of the Nile River Basin. You know that it's the longest river in the world that's crossing 11 countries in northeastern Africa. It has two sources. The White Nile contributes about 14%, and also the Blue Nile, which contributes about 86%. So most of the flow is coming actually from the east, from the Ethiopian highlands. This map is also showing the different dams in the basin. So the green triangles are reflecting the existing dams. So there are about 11 existing dams. The red triangles show the planned dams or dams that might come in the future, and there are about 35 planned hydropower dams, and this is based on this database from Zarf et al. In 2015. And also the yellow triangles, which represent the under construction dam. And one of these dams, which is making the changes now to the basin, is the Grand Ethiopian Renaissance Dam at the border between Sudan and Ethiopia. This dam is currently under construction, and it's expected to be the largest hydropower dam in Africa with a storage capacity of 74 kilometers. And this storage capacity is very big. I mean, even if it's compared to one of the largest hydropower dam here in the US, which is it's called the Grand Coulee Dam. It's like 6 times of the Grand Coulee Dam here in the US. So it's a very large dam, and it's as I said, it will be controlling the Blue Nile, as it's built here in Ethiopia, so to be controlling the Blue Nile flow. So this will introduce many challenges to the Nile River Basin, and there are many challenges. So I'm summarizing here the challenges in the basin, which is facing the water management. So first of all, it's, as I said, it's crossing 11 countries, which is making it as a transboundary river. And so it's very challenging to manage the water or to have sustainable solutions for a transboundary river. And here it's more complicated because it's shared between 11 countries. The second challenge is the data availability and sharing, especially when we talk about developing countries. The data availability is not easy to get to have a data, but even if the data is available, another challenge is the sharing of the data. So most of the data, even if it's available, the agencies which are having this data are not sharing it or not making it accessible for the public. The third challenge is a population growth, and as you know, most of the Nile countries, they are having an increasing rate in the population, and even some of the data or the numbers showing that Ethiopia, which is currently is more than 100 million people, they have a projection of about 200 million people by 2050. Egypt as well is more than 100 million people, and this increase in the population will probably causing more challenges for the food and energy demand. So it will induce more food and energy demand. And if we look now at some of the maps showing the nourishment of the food security in the Nile Basin, we will find that 54% of the population in the basin are undernourished. In terms of the energy demand, but this is even for the whole Africa, there are around 620 million people in Africa without access to electricity. Another challenge is the transboundary plant dams, and as I mentioned in the previous slide, one of them is the Grand Ethiopian Renaissance Dam, but even there are other dams that might come in the basin as well. All of these challenges are also complicated by the climate variability, and here what I mean by climate variability that some years might be dry or some years might be wet. So this kind of variability in the climate will reflect into the stream flow, and so introduces more challenges to the water management in the basin. So based on these challenges, I developed this satellite-based blueprint or framework. So it basically has two components. The first is modeling the upstream condition, and then the second is modeling the downstream condition. So the first component, or the upstream modeling, has two parts. So the first part is the hydrologic model, and here I'm using a model called the VEC model, or the variable infiltration capacity model. And then the outflow from this model is the inflow into the reservoir, and in this case, we have a plant dam, or for example, the GERD in my case, or the Renaissance Dam. So we have another part here, which is the reservoir model, and the idea of this model is to build different scenarios for the plant dams or for the GERD. For example, building filling scenarios or operation scenarios, and see how this will impact the downstream. And then for the downstream, there are two other parts. The first part is again another reservoir model, but in this case for an existing dam, which in my study is the highest one dam in the downstream in Egypt. And then the last part is a ET model, or evapotranspiration model. And the idea of this model is to use the ET, or to calculate the actual evapotranspiration, and using this as a proxy of how much water is used for irrigation, or how much is used in agriculture in general. So this is the last part of the model, and as you can notice on all of these parts of the framework, I'm using satellites. So for example, in case of the hydrologic model, the forcings are coming from satellites, like the topography is from the SRTM satellite, the precipitation, for example, using the TRIPS, or I even use the TRIM as well. So most of these forcings for the hydrologic model, I use the satellite. Also for the reservoir models, I use also another kinds of satellites, like Landsat or altimetry, to understand the the relation between the area and the elevation, and also get an idea about the water level or the storage level in the reservoir. And for the ET model, I use another satellite-based approach called the CBAL, or Surface Energy Balance algorithm for land. So it's a very well-known approach for estimating the ET using again satellite, and in my case I use Landsat. So in this presentation I'll focus on I'll focus on the part which is like how the Hayaswan Dam can adapt its operation to the filling and the operation of the GERD. I'll not go into details into hydrologic model. I'm referring for this paper, which is already published, and it's discussing more about how we develop this hydrologic model for the Nile Basin. So for the GERD, some of the questions that we are interested in, the first is how long Ethiopia will take to fill the dam, and for that I developed different filling scenarios, and in my case the filling scenario is how long it will take. For example, if Ethiopia decided to fill the dam in 3 years or in 7 years. So this is, for example, like two different filling scenarios. And then even after the filling, how the dam will be operated. So how, after filling the dam, how Ethiopia will operate the dam. And again, here I developed different operation scenarios. And the most important question for my study is how the Hayaswan Dam can adapt its operation for both the filling and the operation of the GERD. The GERD in general, as I said, is located at the border between Ethiopia and Sudan. It has a storage capacity of 74 kilometer cube. And the average or the median flow is around 47.5 kilometer cube per year. And here I'm just showing the probability versus the annual discharge. So from here, I concluded that the median flow is around 47.5. But I also want to say here that if it's a 47.5, this is a median, or if we think about it like as an average, then the dam at least has to take 2 years to fill. This is the fastest approach to fill the dam, is to fill the 74 kilometer cube, is to fill it in 2 years. And in this case, Ethiopia is kind of storing all the water which is coming from the upper Blue Nile to fill the dam. So in my study, I tested different filling scenarios starting from 2 years up to 12 years. So the approach I followed to find a way to adapt the Hayaswan Dam, I use a stress metric called the water supply stress index. And the water supply stress index, it's simply the ratio between the water use and the water supply, or the water consumption and water supply. And as you know that most of the water in Egypt is used for irrigation, and it's more than 85% of the water is used for irrigation. So I focused here in the water consumption in the water used for irrigation. And to calculate that, as I mentioned in my framework, I'm using satellite approach, and I use a CBAL to calculate the ET, or the evapotranspiration. So here the y-axis is showing the monthly evapotranspiration, the x-axis is showing different months during the year, and every line here is showing the ET for different year. So I did it from 2014 to 2017, and the black line is showing the average. And I see that the CBAL approach is able to capture the 2 seasons of irrigation in Egypt. One of them is here by the winter one, which ends like around March or something, peaks around March, and the other one which peaks in August. Then the second component in the WASI, or this stress index, is the water supply. And here again, I calculate the water supply for the 4 years from 2014 to 2017. And how I did that, I did it using the satellite-based framework, which I didn't show it in the presentation here, but it's discussed in the paper that I referred in like the previous slides. But simply, I use a satellite approach as well here to do a water balance for the Hayaswan Dam. I have, like, for example, I have the inflow from the hydrologic model and have the water level from the altimetry. So using the water level and the inflow, I did a water balance approach and see how much water is released from the Hayaswan Dam. And we did this for different years. And then the black line is showing the average as well. So once we have the water consumption and the water supply, we can calculate the water stress. And the water stress here is showing how much of the water which is supplied is used for irrigation. And there is a high stress during the winter months, especially after maybe September up to March. The stress is high, which means that most of the water which is released from the highest one dam is used for irrigation. But what also I found is that during the summer, the stress is very low, which means that some of the water which is released, actually most of the water is released during the summer is not fully used for irrigation, which open the opportunities that there are a chance for the highest one dam to adapt its operation, especially during this period during the summer, because the stress is very low. So here I tested different scenarios. So if we focus on this table, the table is showing the scenarios that I'll be showing here for the GERD filling, the 3-year filling scenario versus a 7-year filling scenario, and both of them are reflecting a fast versus a slow filling scenarios. And then the initial highest one dam level, highest one dam storage level, which is reflecting the conditions at highest one dam. So I tested also 2 different scenarios, a low level, which is around 169. I just considered here the level for highest one dam in the last 10 years. So in July 2012, it reached 169. And another scenario is at the very high storage level, which was in 2019, it reached 179. And then the third factor is the water stress index, which is reflecting if the highest one dam will adapt its operation or not. And here the non-adaptive approach is using the same stress levels that I showed in the previous slide, versus if highest one dam is considering adaptation or adaptive approach by changing the stress during, for example, the summer. And if I just go back and show you how we change the stress is, as I said, in the summer, there is a low stress, which means that the highest one dam is releasing more water than that used for irrigation. And so my idea is like, okay, so why not highest one dam try to store more water, especially during the summer, and release less? And to do that, we need to elevate the stress a little bit. So, for example, if it's 0.5, we can push it up to 0.7 or something. And when we push it up to 0.7, it means that the highest one dam will be storing more water and releasing less. So this figure is showing the results for these different scenarios. So the y-axis is showing the highest one dam level. The x-axis is showing the time of the filling of the GERD. So if, for example, if we focus on these two panels, it's showing for a 3-year filling scenario, and the upper panel is showing for the current stress condition, which is the non-adaptive approach, versus if we change the stress, which is the adaptive approach. And as I said, the y-axis is showing the time of the GERD filling. So this is the 1st year, 2nd year, 3rd year. What we see here that yeah, and one more thing, actually, the line, which is the thick line, is showing the scenario of the high initial storage level for highest one dam, and the thin line is showing the low initial storage at highest one dam. So what we see here in both cases, the high or low storage level at the highest one dam, the level will go down or will decline by time, and it will reach a very low level by the end of the 3-year filling scenario. And I explained this in terms of the trend slope, or the slope of the line. We can see the slope of the line is negative, which means that there is a declining in the highest one dam level, which is expected. But what is also important here to see that the level can go down actually to around an average, it can go to 160 or something. This is in case if we are not following an adaptive approach. In case if we follow adaptive approach, it can go up to 165 or more than 165 on average. But again, this is for the scenario of the low storage level. If we consider a high storage level at highest one dam, then it might go down up to between 170 to 175 or something like that, which is not bad in this case. Again, if we look at the 7-year filling scenario, it looks much better, and it's actually showing that the highest one dam, there is no that declining in the highest one dam level, but it can be even flat. One more thing I'm showing here is the standard deviation, which is important because it's reflecting the climate variability in the stream flow, and we can see that it's important because in case if it's a very dry years, then we are expecting that the highest one dam level by the end of the GERD filling, it might go down to very low levels. And even here, if you see these gray lines, it can go to around close to 150, which is very close to the minimum operating level of 147. So some of the key points here that there is a drop in the highest one dam level, especially for the 3-year filling scenario, but a flat pattern is noticed for the 7-year filling scenario, and significant improvement can be noticed if the GERD starts while the storage level of highest one dam is at a high level. Another dimension for the problem is the GERD operation, and here I'm looking at something I call the recovery for the highest one dam. And what I mean by recovery here is how long it will take for the highest one dam to return back to its normal operation. So the normal operation is, I defined it as to reach the level of 175. And we can see here it depends on different scenarios. For example, if we look at this 3-year filling scenario, for example, by the end of the 3-year filling scenario, the highest one dam level might be at a level of 157 or something. So how long it will take to go back to 175? In this case, it might take up to 11 years. So this is just an illustration for how I define the recovery period for the highest one dam. And again, as we change the stress or changing the filling scenario, we expect a different time or different period for the recovery. So this box plot is showing the recovery period for different filling scenarios. So the x-axis is showing filling scenarios from 2 years up to 12 years. The y-axis is showing the number of recovery years for highest one dam level. And then each plot is showing different conditions. So here, for example, is showing the current stress conditions and low initial storage level. So if we look at the 3-year filling scenario, we can see that the median is around 10 or 9 years of recovery. But also the box plot is reflecting the stream flow variability. So if it's a wet versus dry year, for example, if it's a dry year, it can go up to 25 years until the highest one dam recover back to its normal operation. Again,
you have
yes.
2 minutes.
Yes. Okay.
You have 2 minutes.
So, okay. Yeah, I think I have one more slide. So the last. This panel is showing it's a very optimistic scenario if we consider adaptive approach with a stress level of 0.7 and the high storage level at as one dam, then the recovery period is mostly less than 5 years. So the key findings is that the filling scenario greater than 7 years has less impacts on highest one dam operation. The highest one dam operation can adapt to the GERD filling, especially in the summer months. But the most important is actually that the 3 countries have to foster the negotiation to agree for a long-term framework. And this framework, it should work for the GERD, but not only the GERD, but also the transboundary projects in the basin. Some of the future direction is trying to use now the forecasting information and to adapt the reservoir operation, and also building a decision support system to include all of this work into a decision into an operational system. And I built this system, it's called NEBRAS. So it's based on the satellite frameworks that I showed, and it has different tools. So you can go and check this system. It monitors the reservoir operation, and this is operational now. So whenever you go there, you can see how much of the water is coming into the dam, how much of the water is released. There are other tools as well that you can investigate into if you go to this system. I think I'll stop here. I just want to thank some of the funding agencies for my research, and Yeah, I can stop here. I mean, I'm not sure if you are taking the questions now or we will wait for.
Yes, we will open the floor for question. We can receive now a few questions for the next 5 to 7 minutes. So if any of our colleagues from the participant would like to have any question to Dr. Hisham on this interesting and comprehensive presentation, please raise your hand and we can open the floor for the question. I couldn't see any hand raised up till now. Also, I couldn't see any question on Q&A. So if there is no question for Dr. Hisham, we will move ahead to the next presentation. So I would like to invite my colleagues, Dr. Kamran Somoro from Pakistan, for the next speech and next presentation. Mona, if you can show the bio for Dr. Kamran, please. Yes, Dr. Kamran worked as a senior scientist at Plant and Production Center of PARC at Karachi. He is 15 years of experience in agriculture, water management, including soil salinity, high efficiency irrigation system with solar pumping to improve the water productivity. Water productivity is one of the most interesting topic at present. He has also participated in various national and international training seminars and courses and conferences in the United States, Australia, China, Malaysia, Sri Lanka, Philippines, and Thailand. His speech will be about the assessment of the soil salinity and on-soil profile using drip irrigation technology. Dr. Kamran, the floor is yours. Please, you can share your presentation and start.
Okay. Thank you, Dr. Daud. As my introduction was done, can you hear me?
Please go ahead.
Okay, yeah. So I'm just going to discuss about the assessment of the soil salinity in soil profile while using the drip irrigation technology. Here is the content of my presentation which I'm going to present. First, I'm going to introduce the background. Then I will show the research aim and objectives. Then I will discuss something about the methodology which we used. Then I will show the results and discussion. Then I will conclude my presentation. As we know that the water scarcity and the salinity has a severe constraints globally and specifically in arid and semi-arid climate, and more than 75 countries are dealing with the challenge of salinity, including Arab countries, Pakistan, those who comes under the arid region, and has the adverse effect on the soil fertility. The food security, the big challenge we are facing here, the nexus, like the food, water, and energy. So we have to focus on the water and energy and the relation between them. So in South Asia, as we know that the most populous region of about 1.74 billion people. So these are not only people, basically, these are the customers which need food, water, and energy. So we need to think about their food. So here is the objective, just to see assess the effects of saline groundwater on bitter gourd yield using drip irrigation system. Here we have used basically the bitter gourd crop, which is the moderately saline crop, which we can grow in the under saline areas as well. Then to evaluate the effects of saline groundwater on soil salinity status after the end of experiment. Here I would like to clear that the project location basically in the Karachi is the metropolitan city. So it comes under the urban agriculture and there is no any access of the canal water. So the only source here for the water is the groundwater, and which is going to deplete and desaline. So this is the way which we are doing. So here is the methodology I'm going to share.
Would you please share your presentation? It's not showed on the screen.
Sorry?
Mona, can you mute yourself, please, Mona?
Yeah, sorry.
Please,
So for
Dr.
the chemical analysis, we just include the electrical conductivity, which is the measure to show the salinity status in the soil and water. Then the
Dr.
pH.
Kamran, you didn't share your presentation.
Sorry, I cannot share. No, should I share my presentation or not?
Yes, please.
No, I'm sharing basically, but I don't know. Let me.
Mona, can you help us to allow Dr. Kamran to share his presentation, please?
Is it fine?
It's coming now. Go ahead. Yes, Doctor.
Okay, sorry.
If you can put him in the presentation mode, please.
Okay. Thank you. So, sorry. So the soil texture, which was determined by the Boyka's hydrometer method, and electrical conductivity was determined by the digital meter, which we have available at the Karachi PRC station, and the pH was recorded by the digital pH meter. This model was shown by and recommended by the Richard 1969. Sorry, I think it's go back. So the sodium adsorption ratio here just show the chemistry. I'm not going in detail. The equation which was calculated by these equation, the exchangeable sodium percentage was calculated by this equation. And then we got the crop yield. The crop yield, basically, there were two plots in my research area. One, we were irrigating the fresh water. That was the electrical conductivity 0.56 something. So that was bit fresh, and it is also the groundwater, while the other was the saline, which has the high EC, that was the 2.56. So that was the two seasonal crop, because bitter gourd can be cropped in consecutive season 1 and 2. Then we got the crop yield from different plot. So the crop yield was calculated by this formula in kilogram. We got the in plots, then divided by the area, which was in hectare. So how we calculated the soil salinity assessment? Here, this figure, you can see that this is the lateral line of the drip irrigation system, and here is the emitter. So here the water comes, this is the canopy, which makes naturally when the water comes. So this is the wetted zone, and this is the wetted periphery. When you apply the intermittent, the irrigation, you see the salt's appearance in the wetting zone. So basically, as I mentioned, that the two qualities of irrigation water into different plots were used to grow the bitter gourd using drip irrigation to observe the change in soil EC, pH, and SAR. Then the samples before irrigation was taken, and to make a composite sample like 0 to 30 and 30 to 60 centimeter of depth. Usually the bitter gourd crop roots go laterally up to 60 centimeter, not more than that. Then we took the analysis for the wetted zone and wetted periphery. Next. So just come to the result and discussion. As I mentioned, the soil texture, these were the two different plots. One was irrigating with the fresh water, while the other was irrigating with the saline water. The dry bulk density was the 1.58 gram in centimeter cube. Then the other plot, which was irrigated with the saline water, that was the 1.56 gram per centimeter cube. The infiltration rate was almost same as the sandy soil in nature in this area, because we are just almost close to the sea. That was the around 200 kilometers away the sea. The field capacity is almost same, 14.7 and 6 in percentage. Wilting point was 6.2. The available moisture was 8.5 in percent. So here is the crop yield. We were using with fresh water, that is irrigation treatment 1, and with the irrigation treatment 2. Here clearly you can see that the fresh water shows the remarkable yield in different season in comparison to the saline water. But not that saline, as the bitter gourd I mentioned that the moderately saline. So we took some yield as well in comparison with fresh. No doubt it was not that much apart from that, but we took some yield on it as well. So here to see the effect, as my objective was to see the impact of this saline water on EC before and after the experiment using drip irrigation system. Because the water comes with the drip irrigation, with the drop by drop, so just we see the impact on the soil. So here is the mean of two plots at the different depth. As I mentioned that my target was to 30 to 60 centimeter. You just see the bit small changes in the first season. That was the in wetted zone. You can find the EC was 2.4 decisiemens per meter, but in season one, while using the saline water, you can see 2.6 electrical conductivity. That was in decisiemens per meter. While in season two, as the bitter gourd is a summer loving crop, but here we also use, because in Karachi we are just different from the whole arid region, that we can grow this crop the whole season throughout the year. No doubt the yield was bit lower in comparison to season one, but as far as salinity is concerned, because to check the salinity status, we just need at least 2 rotation of the crop to find the actual result. So here we can see that in wetted periphery, as I showed in figure, that the wetted periphery in season 2, while using irrigation treatment to the saline water, the wetted periphery was the 5.6 decisiemens per meter. This is very high salinity. So similarly, at the depth of 15 to 30, it was 5.8, and similarly in 30 to 60, we got 5.8. Like this, we also see the pH. pH usually has not, not changed suddenly. pH usually requires at least 4 to 5 years when you are cropping under saline areas as well, because it do not sudden change from 1 or 2 seasons. It takes 4 to 5 years to change in soil. So here you will not see the big change in EC, because the average of 2 plot was 7.2, and in wetted periphery it was the same, in season 1, while in season 2. Similarly, in season 2 and irrigation treatment 2, you can see a big change. That was the 7.5. It is again under the normal, not that kind of change. Similarly, I'm not going to discuss the sodium adsorption ratio here, because we can see the same trend here. So just in the 5.1 on the 0 to, because this is the upper surface 0 to 15 centimeter, because here in Karachi region, the Pakistan, the arid area, the evaporation rate is very high. So we are focusing on the wetted periphery areas. So I'm just going to conclude that as the salt accumulation at the wetted periphery, did not affect the agronomic parameters. As I mentioned that we also got the same yield, but a bit low. Sometimes we got the good fruit size, the plant size, and in the weight size. Then crop yield of bitter gourd by using drip irrigation method. The pH in soil after experiments 1 and 2 remain unchanged, as I showed in figure, in the wetted zone and wetted periphery under both irrigation systems, due to the fact the buffering property of the soil in nature. And in future, we also recommend that this crop can be grown under the marginal environment, under the saline condition in the arid region. Thank you for your time.
Thank you very much, Dr. Kamran, for this is a comprehensive presentation, and actually one of the topic of the hour, using a new innovative technology for irrigation to save water. But what will be the impact, the environmental impact on the soil, salinity, and the accumulation of the salts if we use dripping irrigation or sprinkler irrigation or even subsurface irrigation system? I will also would like to open the floor for a few questions for the next 10 minutes. If any of our colleagues from the participants have any question, I know that there is not allowed to raise your hand or something like this, but if you face a problem raising your hand, you can write your question on the Q&A area, and we will receive it and forward it to Dr. Kamran. So please, if you have any question, you can write it down on Q&A area. Any question to Dr. Kamran? Right. Also, to I will leave the question and discussion is open. Then we will forward the question at the end of the session to all the participants. So please write your question down on the Q&A area, and we will forward it to Dr. Kamra and other speakers at the end of the session. I would like to invite the third esteemed speaker in this session, Dr. Mohammed Nouer. Dr. Mohammed Nouer is Associate Researcher of Irrigation and Hydraulics Department at Civil Engineer and the National Water Research Center in Cairo, Egypt. He's interested in energy management and water sector. He was graduated in 2010 by excellent grade with honor degree and ranked one of the first in his class, actually. Teaching assistant at Department of Civil Engineering at Shuruq High Institute, Cairo, Egypt. He got his MSc from the Faculty of Engineering at Ain Shams University in 2016 and published many papers in different national and international peer-reviewed journals. He will speak today, Dr. Nouer, about the applied solar bonds as a reduction measures for the NEXUS energy concept. Dr. Nouer, the floor is yours, and you have 20 minutes, please. You are muted, Dr. Nouer. If you can unmute yourself and share your screen presentation, please.
Okay, Dr. Dawood, thank you for this presentation. And good afternoon, everybody. Good afternoon, ladies and gentlemen. Thanks for Dr. Dawood, and we'll share my presentation now. Applied solar bond as a reduction measures for NEXUS energy concept, presented by Mohammed Nouer from National Water Research Center. This picture shows the Egypt in the Egypt population is concentrated in narrow strip of fertile land along the Nile River, concentrated approximated 80% from total land in Egypt. The Nile is important for people in Egypt. Sustainable power, renewable energy are key for climate neutral the future. This figure shows water, food, and energy NEXUS to improve the life and facilities. Challenge: increased demand for food. Food demand is expected to increase by 60% in 2050. Increased food demand is caused by population growth. Another challenge by increased demand for fresh water, where fresh water need an increase by 55% between 2000 and 2050. Demand is driven by agriculture, which account by % of global freshwater use, and food production will need it to grow by 70% approximated in 2030 to feed the growing population. Salinity limit, where yield of agricultural crop, especially in arid and semi-arid zone, climatic zone like Egypt. Another challenge is increased demand for where energy needed increase by food sector to account for around 30% of the world from total energy consumption, and increase food by 60% will lead to an increase in energy consumption in agriculture of 84%. Also challenge is ground greenhouse gas emissions, where ground has emissions, are expected growth by 50% by between periodic in 2012 and 2050 are mostly driven by energy demand and economic growth. In 2050, carbon dioxide estimated will be duplicate approximately greater than 1990. Some application to get clean energy by solar bond technique, clean energy by the sun, conventional, and the storage from layer to water layer, where the storage zone by saline water and isolated by fresh water. The lower zone is a storage zone, where the storage zone needs saline, where increased saline, increased temperature. And we will physical model of solar energy by solar bond technique applied in Fayoum Governorate in Egypt. Application of solar bond in Egypt of solar energy at thermal water up to 70 degrees centigrade, and the storage of heat can be transport the thermal heat out of the system. The thermal water, industrial or agricultural process, or can be used salination or building heat or and generate electricity, can be where can be get up to 70 degrees centigrade available on hour per day. Firstly, this is Egypt map. The control point from NASA each to have degrees, like this point, this green point. This is Egypt control point. Can we get the DNR as direct normal radiation, where NASA have recorded data from 30 years up to 2013, where this map, this conclusion of 30 years and can be show the direct normal radiation map, wind map, and relative humidity percent map, where the can be show the relative humidity in upper zone and lower zone is less than relative humidity. This factor effect on solar bond technique. Data processing. This categories of factor impact in Egypt and impact in solar bond, where DNR, direct normal radiation, where increased direct normal radiation increase the efficiency of solar bond and increase the power. And in Egypt have 6 categories. When increase direct normal radiation and temperature can be good in implemented in solar bond technique, but wind is negatively impact in solar bond. This maps is show available from this table, and when intersect all these maps can be get suitable location for solar bond technique as show map. This is best location for implemented solar bond technique. In field measurement and implement solar bond can be implemented in Fayoum governorate. In Fayoum governorate, we have Shakshuk Research Station in National Water Research Center. Shakshuk Research Station with area equal 10 faddan, mostly 42,000 square meter. Satellite image for the station, and we implemented the master solar bond equal 12 areas. In Shakshuk Research Center have Karun Lake. Karun Lake is a saline lake and have more than 1,000 ppm sometime. Experimental work in Fayoum, experimental program for implemented of experimental program for bond equal 12 times 12 meter, and the selection for material and collect data and sample for this. Firstly, we have weather station like the pictures. Weather station can be get time and temperature, direction of wind like that, and wind speed, and so on. Can be calibrated of NASA data from NASA, because data from NASA equal 5 to 5 degrees centigrade. Firstly, measurement of evaporation measures like that, and sample, collect sample, and we have benchmark and surveying tools like total station and leveling and benchmark like that in the station. Implemented and data collection where the digital thermometer can be calculate the thermal water and salinity measurement like that. This quality control and assurance for pipeline. This bond implemented in Fayoum, Shakshuk on Karun Lake. This is master bond to get energy. And this is implementation steps of solar bond technique, where geomembrane installation in site like that, and this water network to get the cold water to convert the water and high salinity with high salinity water. Water is cold to hot water. This is machine of needed for welder membrane, and this is a checklist for quality control and quality assurance and welded implemented, and this quality control in lab test figures in where geomembrane tested like that, and welded test like that, and critical for geomembrane is punching test. Geomembrane color effect where is neutral if neutral temperature is 30 degrees centigrade. If use a white geomembrane equal 40 degrees centigrade geomembrane, and if color is black can be get up to 70 degrees centigrade in geomembrane, not water saline. This is photo show implementation. This string needed for damped wind force. The wind force is efficiency of solar pumps, and this machine is loader to and protect of geomembrane installation. This is final implemented of solar pump technique book station in Karun Lake. Test for get sample from Karun Lake and all storage area in the solar pump technique using flame volumeter model 4420. Another machine known chromatography like that, and this sample for test material and test the type of saline in solar pumps and Karun Lake in Karun Lake. This is photo and implementation solar pump in Fayoum Governorate. This is machine to measurement of temperature measurement inside, and inside get temperature up to 17 degrees centigrade, and this profile to show result in temperature profile to get power and energy clean from solar pumps. In solar pump technique have 3 layers: upper layer, lower layer, and neutral layer. In each layer can be get the temperature and up to get 70 degrees centigrade in Fayoum Governorate. This density profile and solar pumps and lead to simulation. Firstly, get experimental program. Secondly, get simulation of solar pump technique like that. In program Transis 17. Program can be simulation of solar pump technique and can be collect weather from NASA and data processing from collection, pump station, and type, and can be simulation and print simulation. This simulation of solar pump technique in Fayoum Governorate, Egypt, modeled by Mohammed Nawir. And this show numerical model in can be storage area up to 70 degrees centigrade by program Transis program 17 solar pumps. Conclusion: ARC is successful tool to reduce solar pump radiation, temperature, wind, relative humidity maps. Solar pump technique is clean energy and decrease the oxide emission. Solar pump potential areas are Faraf Usis and near Dakhla Usis and other places. Solar pump give the heat storage up to 17 degrees centigrade in Fayoum Governorate, according experimental program in Egypt. Climate Egypt has potential for all seasons. The area that potential for solar pond in Fayoum, Egypt can be simulated by Transys program. Thank you for listening to my presentation, Mohammed Nawir, and thank you, Dr. Daoud. Shukran.
Thank you very much for Dr. Noer for this interesting presentation. And actually, we are looking for the future of the solar energy, and the solar ponds are one of the alternatives for using solar in the future. Thank you very much. We will open also the floor for question. We checked the raise of hand option, and it works. So if anyone would like to ask any question to our esteemed speakers, he can raise hand. Down in the panel list, you will find the option for raise hand. You can raise your hand and you can ask question. Until we receive the other question, we do have some question on the chat area and also on the Q&A area. I will start with the Q&A area, which they forward their question to mainly to Dr. Hisham. Dr. Hisham is still with us, please.
Yes, I'm here, Dr. Mohammed.
Dr. Hisham, we received 3 questions for you. The first one is from Dr. Abdurrahman Abdurraouf. And he asked why you are not using this system in Egypt. I think the system, the database system, or the, I don't remember the last system you present in your presentation, Dr. Nader, and why it's not used. Also, we received another question from Dr. Karim Ataya from the National Water Research Center. She said that she thanked you about your interesting presentation, and she said that it's very helpful for the current negotiation between the 3 parties, Ethiopia, Egypt, and Sudan. And would you relate your scenarios to any hydrological condition? How do you think we can persuade the decision makers to use this research results in the future? And also, she would like to have some elaboration on the recovery period of HAD after the operation of GERD, of course.
Okay, so I mean, in terms of the first question from Dr. Abdurrahman, yeah, I think the system, I mean, it's still it's in development, but some parts of this system is currently operational. So when you go to the website, you can see it has the hydrologic model running every day, and it's giving the inflow into the Aswan Dam, or even the hydrology of the currently for the Blue Nile, showing how much water is coming at Khartoum station. And using this satellite approach, I'm showing the storage in the Aswan Dam, the release in Aswan Dam. So it's this part of the system is working, but still other tools in the system, I'm still developing it. But for sure, yeah, we can try to use it. I was planning this summer to go to Egypt and having a small training on this system, but because of the pandemic and the COVID, I was not able to do that. But yeah, I'll try to maybe in the future try to share it with the National Water Research Center or the Ministry of Water Resources as soon, maybe next year or something. The question regarding using the scenarios, I think yeah, we can use these different scenarios, especially in negotiations that are going on. I mean, I showed only three different factors, but there are other many factors that can be included into the work. For example, if we consider the water used by Sudan, if we change the percentage of water used by Sudan or something, and see how this can impact, all of this can be involved in the same work. So it's a scenario-based assessment approach, and we can include more and more other scenarios. The third question is I forgot the Ahmed.
Yes.
The third question, I think, was regarding the.
Yes, this question to me. I think yes. From Dr. Nader Mohammed. Thank you, Dr. Nader, for this question. This question is demand food in 2050 is increased by 60% from only 20 to 30 water. Where the water demand and food demand is increased year by year, where increased population and Dr. Hisham Dardiri can be discussed the challenge in a Nile River basin. This Nile River basin is challenge from increase the demand food, and where demand is increased day by day, where population increase and electricity increase, and this electricity, some electricity get from foil, and foil get carbon dioxide emissions increase day by day. If constant this increase demand will get problem, and I think this statistics and probability like scenarios, if optimistic and pessimistic, or most likely, this all statistics have from FAO, from some papers get number. This not actual number, but this scenarios from 2050. Thanks, Dr. Nader, for question. And any question, please? Dr. Mohammed Dawood.
Thank you very much for Dr. Noer. We still have some few questions again for Dr. Hisham and also for Dr. Kamran. I will start with two questions to Dr. Kamran. Dr. Kamran, we received two questions on your presentation. The first one says that we have high percentage of iron, more than the standard. Is this will affect the growth of the plants? And the second one, are there any standards value for iron percentage for each Ki and C of plants? Please advise.
Thank you, Dr. Dawood. Yeah, we have the limitations and we have the standard values basically for the different crop. But again, it depends on the soil condition. Like when we talk about the arid region, if we have sandy soil, so we can use basically the saline water, because the salts basically leach down with particles, but the same scenario will not apply in the clay loam soil, as it has the holding capacity, so it affects the plant growth. So again, it varies. So that's why we also need the soil as well as water analysis for each plant, and every crop has their own requirement. So we have the standard vegetables like guava, chiku. These are also the orchard plant we can grow under the saline environment.
Okay, thank you very much. She asks also about if there is any standard or guidelines for the percentage of iron.
Sorry?
There is a question also about the guidelines or standards for the percentage of iron in the soil.
Yes, definitely. There are some standard percentage of the cations, that is the calcium carbonate and bicarbonate in the soil, which also affect the crop yield as well, because if the soil is not that kind of fertile, sometimes we do not get the better fruit size. So sometimes it has the potassium deficiency or the nitrogen deficiency. So definitely there are some standards for the different crops, and different biological standards are there.
Okay, thank you very much, Dr. Kamran. I have also another 3-4 question for Dr. Hisham. The first one, I will go through them one by one, Hisham. The first one, what about the hydrogeological condition during the filling years? Is it average, dry, or wet? And how will be the impact of this hydrological condition on the operational of GERD and its link with the highest one dam?
Yeah, so for the first question, the hydrologic condition, I did consider that when I was showing if you remember the plot for the highest one dam level, I'm showing the error bar. So the error bar is indicating these hydrologic conditions, if it's a dry or wet year. And as I mentioned in my presentation, for example, if it's a very dry year, the highest one dam will go down to very low level, might go even to 150 or something by the end of the 3-year filling scenario. So I did consider this.
Good. The second one, she mentioned that in your finds, you mentioned that the 7-year filling scenario has less impact on head. That's right, but will be better to link the filling of the GERD to the hydrological condition and not to fix a number of years? She would like to speak about the change in the hydrological condition within the Blue River Basin and not both specific years for filling 7, 11, 2, 3, whatever. But we say in the high floods we will store more. They can allow to store more, but in the dry seasons and dry floods we will not allow. We should not allow Ethiopia to fill and to store more. So
yeah, I mean I know there are different ways to do the filling. I mean, there is one way which is like if they negotiate for a fixed release every year or something. So this is a different approach of filling. So the way I did it is that to do based on the years, which is kind of going to the side of what Ethiopia wants to do. It's more like a worst case scenario that Ethiopia is deciding how many years it will take. But yeah, that's true. We can also do it in the way that, and I think there is a paper by maybe Kevin Wheeler in 2016. He did that he changed the scenarios based on the release decision. Like if Egypt said like Ethiopia has to release every year maybe 40 kilometer cube per year, then this is another way. But yeah, we can consider that as well. But in my case, I just consider the filling scenario. But by the way, I took the hydrologic conditions again in the filling scenarios by doing I mean a moving window or something like that can consider also dry and wet years, but it's still based on the number of filling years. Which, yeah, but yeah.
Sorry, the third question to Hisham, you mentioned that head will recover after 12 years in 3 years filling scenario. I think you didn't take into your consideration or account the increase in Sudan abstraction or withdrawal during the operation of GERD, as Sudan is expected to abstract or use more water because of the regulation of the Blue Nile and the fixed flow or the from the release flow from the GERD.
Yeah, I think that's true. And one thing I mentioned, I was doing a scenario-based assessment, and there are many factors. So one factor is, as it's mentioned here, that South Sudan abstraction can increase in the future, which is also very important to consider. But I mean, there are many factors we can consider, and this is one thing we can also consider in the future. But I showed again the box, but when I showed the box plot, it doesn't mean that it's 12 years, because 12 years is just the average. But if you consider the stream flow variability, I said that in case of 3 years, it can go up to 25 years or more than even 25 years. So, but this considering the stream flow variability, but if you consider also that Sudan use will increase in the future, yeah, this number of years will increase.
Okay, the last one is just like comments. It's not a question actually. They said that you have to take into consideration that the head is multi-year storage reservoir, not annual operational reservoir. طبعا يعني خزان استراتيجي. So head can adapt its releases from year to year, but GERD also have to take mitigation measures during the drought periods to support head.
Right.
Yes. Is there any other question from my colleagues from the attendees? We are willing to receive more 2-3 questions to the panelists, to the speakers. Until we received any question, and we do have about 10 minutes before the closure of this session, I have 2 questions. The first one for Dr. Noer about the future of the solar ponds, Dr. Noer, in the region. Do you see it as an alternative, visible and environmental friendly visible technology, or solar photovoltaic and concentrated mirrors will be the most suitable option in the future compared with the solar bonds?
Yes, thanks, Dr. Daoud, for this question. Future in solar bond is good because the solar bond is clean energy, and this solar bond system and technique can be solved of problem by the brain problem. Brain from manufacture of salt manufacturers get brain. Brain is some salt is not good for domestic for people domestic can be used in solar bond technique to solve this problem. And solar bond technique can be get clean energy and can be get from Fayoum governorate can be get solar energy up to 70 degrees centigrade in thermal water. But if you used in الوادي الجديد or best location according to NASA will get more than this energy to get clean energy for electricity and other application. Thanks, Dr. Daoud.
Thank you very much, Dr. Mohammed. My next question actually to Dr. Kamran. Dr. Kamran, recently we hear about the subsurface irrigation system, either the subsurface dripping or the leaky pipes. Do you have an idea about the visibility of this new and innovative technology in irrigation, and what is the viability of them technically? Are they technically viable, and what is their impact on the soil salinity and the growth rate of the plants? What will be the challenging cons and the pros for this two innovative technology compared with dripping and sprinkler?
Yeah, while comparing the drip irrigation technology, in fact, when I was in Australia for my PhD research, we took some subsurface drip irrigation system, but subsurface drip irrigation system is suitable in some areas, not everywhere. It is not that suitable for the saline areas because the life of pipe, let's suppose if we apply to the surface area, it takes 10 years or more. But when we these pipes for the subsurface drip irrigation system, usually the salinity impact, this is the main drawback of the subsurface drip irrigation system. The pipe choked and the emitters is clogged. So this is the drawback. We cannot use subsurface, but it varies again. If the water quality is good, then you can use the subsurface because it's good.
Thank you very much, Dr. Kamran. The last request actually from our colleague, Dr. Tahani Slate from the Nile sector. She would like to request the presentation of Dr. Hisham Al-Dardiri. She would like to get a copy in her, and she put her Yahoo email on the chat. We can send it later to Dr. Hisham, and if we can get a copy from his. Also, I think this session is recorded by our colleagues in the ministry, and it will be allowed shortly either on YouTube on the Cairo Water Week website.
Sure.
So it will be allowable. Also, the presentation will be allowed and accessed through the Cairo Water Week website. Is there any question? Our colleagues from the organizers, Mona, do we have any question on the QA area or chat area? I couldn't see it, Eri.
Not yet.
Not yet. So if this is the case, I would like to thank our esteemed presenter today. I would like to thank Dr. Hisham Al-Dardiri. Thank you very much, and we're wishing you all the best in your research in Washington. And we would like to hear new and good news about your finishing and completion of your PhD thesis, coming back to Egypt to work with us. Dr. Mohammed Noor, thank you very much. Dr. Kamran from Pakistan, thank you very much for your interesting presentation. Thank you for you all. And
You're
we will
welcome.
be in touch with you, and we wish to see you many and many times inshallah, in the future and cooperation in the future. Thank you for
Inshallah,
all
hopefully.
attendees. Thank you very much.
Thank you.
Thanks for you all our attendees today, and thanks for your valuable question and your interaction with the presenter. Thanks, and we would like to see you again in another session, another event. Thank you very much.
Thank you. Thank
See
you.
you. Bye bye. Ma salama.
Bye bye.